Hello everyone and welcome to a new lecture about artificial intelligence. Today we are exploring how AI tackles complex problems using search techniques. Think of it like finding your way through a maze. AI uses clever strategies to navigate challenges like puzzles, navigations, or even game strategies. In this lecture, we will see what is search, what are the type of AI agents that we use for search, what are the key algorithms, and also we will see some real-world examples like the eighth puzzle. Here is what we are going to cover today. We will start with the basic of problem solving by search as a category of AI. Then we will look at different types of AI agents and we will see how they use search. We will dive into the search algorithm. We will explore classic problems like 8 puzzle and 8 queens. And also we see how search powers real-world applications like GPS navigation. By the end of the lecture, you will understand how AI systematically finds solutions. So let's get started. In the previous lecture, we learned about four main categories of AI. The first one is problem solving by search. This category includes algorithms like A star, BFS, DFS. These algorithms are foundational for tasks like pathfinding or game playing. This category is a core part of AI for solving well-defined problems. We learned about the other categories like knowledge, reasoning, and planning, learning, and also communication, perceiving, and acting. In the next lectures, we will discuss them one by one. So what exactly is problem solving by search? In AI, it's about systematically exploring possible solutions to find the best path to a goal. Imagine you are solving a maze. You start at one point, you try different possible paths, and your aim is to reach to the exit. This is the goal state. The core idea here is to model a problem as state space. It means we define all possible states like positions in a maze, and also we see the actions. What are the actions? Actions move you between one state to another state. Then the goal state is the what we are looking for example, exit. So the definition is in problem solving by search, AI techniques that systematically explore solution to find the best path to the goal state. What is the core idea? We want to model a problem as a state space. It means state, action, and goals, and we search for optimal or satisfactory solutions. So in here, we have agents. What is the agent? Agent is an AI system, and this AI system models a problem as a state space, and also it uses search algorithm to navigate from an initial state where we start the game, and we want to go to the goal state, the final state, right? And here, what is the objective? We want to select optimal actions that redirect us to the goal state. Now, let's talk about AI agents. Agents are systems that perceive their environment and act to achieve goals. There are five main types, and some rely heavily on search. We have simple reflex agents. These simple reflex agents react to what they see. For example, thermostat, and here we don't have search. Then we have model-based reflect agents. These agents track the world's state like a vacuum cleaner, but they use minimal search. Then we have goal-based agents. These kind of agents are where search shines. They plan path to specific goals. For example, GPS finding a route from one place to another place. Then we have utility-based agents. These kind of agents, they go further. They use search to optimize outcome. For example, chess AI that they pick the best move. And finally, we have learning agents. These agents can use search to improve our time. For example, a robot learning a maze. Here are some issues that can be resolved using search. For example, 8 queen puzzle. The 8 queen puzzle, in this puzzle, we want to place these queens in such a way that they cannot kill each other, right? So you know, in chess, this queen can kill these directions, so there should be no other queen in here. Or for example, this one can kill up to here, so there must not be queen here. So the problem here is how you can place 8 queen in a chess, 8 by 8 board chess, where no queen can kill the other. This is one problem. Another problem is 8 puzzle, right? So we have this one, and here we want to sort it out. For example, we want to have a 1 here, 2, 3, 4, 5, 6, 7, 8, right? How you can move them. with minimum movements or very fast. Or Sudoku, you know that there should not be the same numbers in here, the same number in here, the same number in here, right? So this is the Sudoku. Or crossword puzzles, or Rubik's cube, or Tower of Hanoi, right? So how you can move all these blocks into here in the same order, and you can use this one as a helper or temporary. But the problem is we should not have smaller down of a bigger one. So it means if this is one, two cannot be here, right? How you can move them here. And this is the Sudoku game, and this is like chess playing. So these are the problems that we use search algorithms to solve them. Here we go. So this is one initial state, and here is the goal state, right? So what are the possible actions? For example, in this state we have three actions, right? So we can move 5 to here, we can move 6 to here, or we can move 7 to here, right? So if you move 6 to here, you go from S0 to S1, and this is the S1, right? So in here, what you can do, you can move 2 here, 8 here, 4 here, or even 6 back, right? So this is the states, right? So you take an action. So you can take action A0, it means you move 6 here, then you will be moved. The environment is changed from S0 to S1. Then you have to repeat and repeat again and again to finally solve this problem. Or we have something called as crypto arithmetic problems. In here we have some letters, right? Send plus more is money, right? Every letter is a representative of a number. So you need to find out that every number that is here is represented by a letter, and also two letters cannot have the same number, and also this addition must hold. For example, S can be 9, right? E can be 5, and also you can see here this E is also 5 here, and this E is a 5 here. So this is the problem, this is the solution. How you can find these numbers for this one. This is called as crypto arithmetic problems. As I said, one is n queen. The challenge here is to place n queens, like for example, in this case, 8 queens, and we want to place them such a way that two queens cannot attack each other. It means no sharing rows, no sharing columns, and no sharing diagonals, right? For example, this one, there must be no queen here, no other queen here, no other queen here, no other queen here, and also no other queen here, right? So how you can place them, right? So for this problem, the state space includes all possible queen placements. And we have action. Action involves placing a queen in a safe position. We may use some backtracking search to try different placement, and also we may go for heuristic search to optimize for fewer conflicts. Another problem here is a river crossing problem. So what is the problem here? You need to get a wolf. So suppose you have a wolf, cabbage, and goat on one side of a river, right? So this is a river, for example, right? So we have goat, we have wolf, and we have cabbage here. And this farmer has a boat, right? Has a boat, and every time it can take some of them here. But the problem is, when the farmer wants to move from here to here, right? He cannot take all of them together because they will eat each other. The wolf will eat the goat, and the goat will eat the cabbage, right? So how we can manage them that they cannot conflict with each other? So it means we cannot leave the wolf with the goat on one side or the goat with cabbage alone because they will eat each other. The state space tracks where each item and the boat are. So we have action here. Actions are moving one or two items across the river. So, for example, one solution is here. First time we have wolf. So if this is the river, so and the boat is here, right? So we have here wolf, goat, cabbage, and goats, right? So the farmer will take the goat this side, right? So goat is here, and wolf and cabbage are here, right? Then the farmer will go back alone, nothing, right? Then from here we have wolf and cabbage, right? It will take the cabbage this side, right? Cabbage, this is cabbage. In here we will have cabbage, and the goat will come back, right? The farmer will take the goat this side, right? And he will leave the goat here, and this time take the wolf this side. So in here we have cabbage and wolf, right? It's okay, they are safe. Then it come back and bring the goat, right? So this is the solution, search using search. Search powers tons of real-world technologies. For example, GPS navigation, they use A star for optimal roads, or robotics relies on BFS for obstacle avoidance in warehouses. In games like chess, the AI uses minimax search with pruning to pick winning moves. Even airline scheduling, they use search to assign crew efficiently. And maybe may go for VLSI, very large scale integration. This VLSI is the process of creating an integrated circuit like IC by combining millions of transistors onto a single chip. So we can go for different kind of problem using search. So the question here is, can we find a closed form for each one? Closed form, it means a formula that can be applied to different situations. So we define the search here. A search problem consists of a state space, the possible states that the problem may have. Then you have successor function. So the successor function, it means when we are in one state and we take an action, then what happens, right? So if we are in a particular state and we take a possible action, then what is the next state, right? Then we have a start state, initial state where we start the problem, and goal state when we want to terminate. So we can call this one as initiate, initialization, and this one for termination. Somewhere we finish it, right? Then our goal is to find a solution, and solution is a sequence of action, or you can call it as plan. This solution transforms the start state to the goal state. It means how we can have a set of or a sequence of actions like a plan to go from initial state to the goal state in an efficient way. For example, in shortest path or fastest time or using less energy or something like that. So let's apply this into the classic problem of eighth puzzle, right? So here we have 3 by 3, right? So 3 by 3. And what is the state here? State is the data representation. For example, we have 3 by 3, the array with numbers from 1 to 8, right? This is 1. And what are the possible actions? Moving left, moving right, moving up, moving down, right? So we have some operators here, and these operators transform state to the next state. So it means when you are in this state, you take an action, so you move 5 here, then you go to the next state. So the next state is this one, right? If you move 6 down, you will be to this state. If you move 7 to here, you will be in this state, right? From one state to another state. Then we have successor function. This successor function generates possible states by applying the operators or action, right? So we apply operators and we return the state whose indices are between 0 and 3. So what kind of algorithm we may use here? For example, we can use BFS, later we will study, or we can go for A star. Search is not just for puzzles, it's everywhere. For example, navigation. GPS systems use search to find the best route from one location to a destination. The state space is a road intersection, and actions are turn or straight moves. And we may use algorithm like A star that uses heuristic like straight line distance to the goal. So here you can see one example, and this example is called that traveling from Arad to Bucharest. This is Romania map, right? And we want to go from one city to another city here, right? So what are the states here? What is the state space here? State space is possible cities. So every node that you can see on this graph, these are cities, or we can call them as state space. What is the successor function? Successor functions are roads. For example, when you are in Arad, if you go to this road, you will go to Zerin. If you go to this way, you go to Sibiu. If you go to this way, you go to Timisoara, right? So these roads are successor function. They go to an adjacent city. And also we have a cost here. The cost is this stance kilometer that right? So in this problem, what is the start state? Is the Arad city, right? Arad city is the initial state. What is the termination or goal state? It's Bucharest when we want to finish it. What is the solution here? The cheapest path from Arad to Bucharest. So how does search actually works? Imagine a search tree where each node is a state. We expand nodes to explore new states, and we keep track of unvisited nodes in a fringe. Later, I will tell you what is fringe. It's a to-do list. The goal is to find the shortest path to the goal with minimum expansion, right? And so here we have a word state, and the word state includes every last details of the environment. Then search state keeps only the details of needed for planning, like abstraction. So problem, for example, pathing, states, XY location from one to another, actions going to north, going to south, going to east, and going to west. What is successor? That update location only. What is the goal? Some city, some location that we want to finish. So state space graphs, we can represent any problem, for example, this one as a graph, right? So graph is a data structure. And in here, we define the state space graph as a mathematical representation of the search problem that we have. So for example, here, so this is the source or initial state. and this is the goal, right, or termination, right? Then we have some node that we can pass through, right? So these are called as word configuration. Then we have arcs. These are called as successor, right? So if you are in S and you take this action, you will go to D. If you are in S, you take this action, you will be in E. If you are in S, take this action, you will be in P, right? So we call them as action result or successor, right? And the goal state is here where we want to finish the game. So let's break down a tree search algorithm. We start with the initial state in the fringe. Then, while the fringe is not empty, we pick up a node to expand. Then we check if this selected node is the goal or not. If not, we add its new state to the fringe. So we have a search tree, right? So if, right? It's a but if tree of plans and their outcome. So we have a start state, initial state, then the children correspond to their successors, right? So for example, here we start. So from here we can go to these nodes, right? Then from here we can go to here, we can go to here, we can. So these are the if we are here, if we are here and we take this action, then we will go to the new state. So this is called as search tree. So in here, you can see the state space search and tree. What is the difference between graph and tree? We have no cycle, right? So in here, you can see here we have a cycle. We can come to here, these are the cycle. But in here, we have no cycle. It's like a tree style, right? So in here, each node is an entire path, right? So for example, here we go from source to the goal, right? This is called as graph, and this is called as a tree, right? So tree is like a tree. We have a root, right? These are the branches, and these are called as leaves, right? The last one is called as leaves, right? So what we do, we use some sophisticated algorithms to start from here, then we try to go for all possible states. Finally, we should reach to this state. And the problem is how we can reach the goal state in minimum time, for example, right? So this is the problem. If, for example, you think of the navigation, you can imagine how big is the tree, right? So the question is how we can traverse this tree in minimum time. It means we reach the goal state in fastest possible time. And here is the 8 puzzle. So in here, this is the initial state, right? So we can go to 3 possible states. It means if we move 7 here, we will go to here. So we can call this one as state 0. We can call it as state 1, right? So if we take this action means 7 to right, right? So we will be here. If we move 6 down, we will be in this state, for example, S2. If we take 5 to the left, then we will go to the state number 3. Then from here, we have 2 states, right? In here, we can go for 3 states. In here, we can go for 2 states, right? You can think how big it is, right? So the problem is how we can reach the goal state in minimum time, for example. And here is from Arad to Bucharest, right? So for example, from Arad, you can go to Zirin, you can go to Sibiu, we can go to this city, right? Then from here, we can go to this city. From here, we can go to this city. So you can imagine this one as a tree, as you can see here. From Arad, we can go to Sibiu, we can go to this one, we can go to Zirin. Then from Sibiu, we can go to Arad, we can go for Arad, this one, right? So we can make this one. So the process here, we expand nodes in a search tree and we maintain a fringe or frontier of unexplored states. The goal is to find the shortest or we can say optimal path to the goal state with minimal node expansions. We may use some BFS algorithm, AS algorithm. Later, I will explain them one by one. So here is the algorithm. This is called as tree search. We receive problem and a strategy, and we return a solution. It means there is a solution, or failure. It means this algorithm cannot find the path, right, to their goal state. So what we do here, initially, we initialize the search tree using the initial states, right? It means we have to start from somewhere, right? So this is called as start state or source, you can see, right? Then we will go for a loop. If there are no candidates for extension, finish, right? So if there's only one state, finish, right? There is no problem. If not, we choose a leaf node for expansion according to the strategy that we have, right? If the node is the goal state, we will finish it, right? So solution, okay. Otherwise, we will expand, right? So, but here you may ask a question that, for example, when we come to here, what is the next one? We will go for this one or we will go for this one, right? This is based on the algorithm. Later, I will explain them, right? So here we have a fringe to save the unexplored nodes. We have expansion and also we have exploration strategy. Later, we will study them. So for example, here you can see what is the difference between search tree and Fringe, right? So we start from source to goal, right? So from S, we can go to D, you can see here, we can go to E, you can see here, we can go to P, right? Then from E here, right, we can go to H, we can go to R, right? From R here, we can go to F. From F, we can go to C, we can go to G, right? This is called a search tree, right? And absolutely here, for example, when we go to D, from D, we should go to B, right? And then from B, we should go to A, right? Then something like that, right? Then what is Fringe? Fringe is a little bit different. Initially, we are only in S. It means we start from here, right? Then from S, we can go to D, right? So S, D. So we can go to E and we can go to P. So these are three possible scenarios. We selected to go to E, right? That's why we highlighted this one. When we are in E, we can go to SER, right? So SER is here. And this is the only one, so we select this one. SEH is here also, so we do not select this one. SER, right? F is here. Then from F, we can go to C, this one, and we can go to G, right? Again, you may ask, why do you select from E to R, not to F? This is based on the algorithm. Later, we will study it. All right, so let's go to the heart of the search, the algorithm that we use. There are two main categories. One is uninformed search or blind search, and another one is informed search or heuristic search. In the case of uninformed search, they do not know how close a state is to the goal. For example, BFS, the BFS algorithm explore all neighbors first, and this guarantees the shortest path but using lots of memory. Or we have DFS that divides deep into one path, and they use less memory but not always finding the short road. Then we have informed search or heuristic like ASR algorithm. It combines a path cost with a heuristic. For example, what is the heuristic here? Estimating distance to the goal, and it try to find optimal path faster. Uninformed search algorithm, they don't have additional information on the goal node other than one provided in the problem definition. So in this case, the plan to reach the goal state from the initial state differ only by the order and length of action. On the other side, in case of informed search algorithm, they have information on the goal state. These help in more efficient searching. This information can be obtained by a function, and this function can estimate how close a state is to the goal state. So here is a comparison between different algorithms. We have, based on we have informed search algorithm and uninformed search algorithms. Based on the basic knowledge, informed search algorithm uses knowledge to find the steps to the solution. However, in uninformed search, we don't have any knowledge. In case of efficiency, informed search algorithms are highly efficient because they consume less time and cost. But uninformed search, their efficiency is mediatory. In terms of cost, informed search, they have low cost, but in uninformed search, they comparatively have higher cost. In terms of performance, they find solution more quickly. However, uninformed search algorithm, their speed is slower. An algorithm, for example, heuristic DFS or heuristic BFS and ASR algorithm, but in here we have DFS, BFS, lowest cost first search. All right, search is not perfect. One big challenge is scalability. So when a problem becomes bigger and bigger, how we can solve using search. For example, the 8 puzzle has 360,000 states. But when we have a larger problem like chess, it goes for billion possible states. There is a lot of nodes to explore, eating up time and memory. Problem solving by search is about modeling problem as state space, and we want to find optimal path. Goal-based and utility-based agents are use algorithms like BFS and A star in order to solve puzzles like 8 puzzle or in queens, or even real-world tasks like navigation. The key is exploring the state space efficiently. Hopefully, you are as excited about AI search as I am. So in the next lecture, we will study those algorithms in details, and we will learn how to code them in Python. Thank you for watching this deep video into AI problem solving by search. See you in the next lecture.